Okay, in this section we will discuss heat exchanger. Heat exchanger. So, what is heat exchanger? Heat exchanger is a device which is used to transfer heat from one fluid to another fluid without mixing. So, this is important, without mixing. There are many types of heat exchanger. So, types of heat exchanger. Types of heat exchanger. Okay. So, the first kind of heat exchanger is a parallel flow heat exchanger. Let us consider in parallel flow heat exchanger the fluids flow in the same direction. Let us say this is our heat exchanger which contains two tubes, one inner tube and one outside tube. So, in the inner tube, let us say hot fluid is flowing, and the outer tube, let's say cold fluid is flowing. Cold fluid is flowing, and let us say hot fluid is entering from this location, entry, and cold fluid is entering from this position. Similarly, hot and cold fluid exits from this and this position. Okay, since the hot and cold fluid are flowing in the same direction, that's why it is known as parallel flow heat exchanger. Fluid or both the fluids flow in same direction. Since there is a temperature difference between hotter fluid and the colder fluid, so as it travels, hot fluid will lose heat and the cold fluid will gain heat. So if we draw the temperature along the axis of the heat exchanger, let us say this is x and this is denoting temperature, and I am saying that the hot fluid inlet temperature is T in and outlet temperature is Th out, and cold fluid inlet temperature is Tc in and outlet temperature is Tc out. So, and definitely Th in is greater than Tc in. So, let us say this is Th in and this is Tc in. So, as the fluid moves in the heat exchanger, hot fluid will lose heat and cold fluid will gain heat. So, we will get something like this, as it will enter at the outlet. So, this will be Th out and this will be Tc out. So, this is the temperature versus axis diagram for parallel flow heat exchanger. The second type of heat exchanger is counter flow heat exchanger. Counter flow heat exchanger. In this type of heat exchanger, fluids flow in opposite directions. So, if we want to draw the temperature diagram along the axis of counter flow heat exchanger, let us say this is temperature, and this is the axis of counterflow heat exchanger. If we draw a counterflow heat exchanger, okay, let us say this is the inner tube and this is the outer tube. Okay, what I am saying, that hotter fluid is entering from here and colder fluid is entering from here, TC in. Since both the fluids will flow in opposite direction, colder fluid will move in this direction and hotter fluid will move in this direction. That's why we call it as a counterflow heat exchanger. Now, if we want to draw the temperature variation, so this will be TH in and this is TC in, let's say. So what will happen? Hotter fluid will lose heat, so its temperature will go down, and the colder fluid will gain temperature, so it will go up. So this will be TC out and this will be TH out. So this is TC out and this is TH out. So this is our counterflow heat exchanger. The third kind of heat exchanger is cross-flow heat exchanger. When we say cross-flow heat exchanger, we mean that the two fluids will cross at a certain point, right? But it will not mix. So let us say this is a series of tubes, okay? If we draw it like this, and we are, so one fluid, let us say hotter fluid, will flow inside the tube and the colder fluid will flow in this direction, perpendicular to the flow of hotter fluid. So this type of heat exchangers are known as the cross flow heat exchanger. Cross flow heat exchanger, and this can be of two types: mixed flow heat exchanger, unmixed flow heat exchanger. So what is mixed flow heat exchanger and what is unmixed flow heat exchanger? So in mixed flow heat exchanger, we do not have control over the flow of fluid which is flowing over the tube. When I say which flow I am talking, this flow. It is not directional, it can move this side also, this side also, right? And when we control this flow, okay, that is known as unmixed kind of heat flow. We will put one plate here, we will put one plate, we will put another plate here. So now these flows, crossed flow, are also guided. So this kind of heat exchanger is the unmixed flow heat exchanger, okay. And the fourth kind of heat exchanger is tube and cell heat exchanger. Before going to the heat exchanger analysis, it is important to know what is overall heat transfer coefficient. Overall heat transfer coefficient, okay. Let us say the overall heat transfer coefficient for a tubular or annular tube is Uy and Uo at inside and outside surface respectively. Then the net rate of heat transfer is given by Q dot is equal to Ui Ai delta T is equal to U naught A naught delta T. And if we remember the electrical analogy, then this can be written as delta T upon R total. From this we can write Ui Ai is equal to U naught A naught is equal to 1 upon R total, or Ui is equal to 1 upon AIR total and U naught is equal to 1 upon A naught R total. So this is one thing. Or I can say U is equal to 1 upon AR total, where A surface area is the respective surface area, either inside surface or outside surface, respective surface area. Since heat exchangers are always in cylindrical form, so let us say this is the cross section of a heat exchanger. Okay, this is Ri, this is R naught, okay, and this is the outer surface of heat exchanger which is insulated. And this is very important, right? The outer surface of any heat exchanger is always insulated. It will not lose heat to the surrounding. No heat loss, no heat loss to surrounding, and this is a assumption. Okay, so if we see here in the inner tube, let us say one fluid is flowing and the another fluid is flowing through this section, and this is the wall of the inner tube. Okay, so the conductance resistance of the inner tube, this can be written as R naught upon Ri upon 2 pi K L, where K is the thermal conductivity of inner tube material and L is the length of heat exchanger. Clear? And as you know, R naught is the outside temperature, outside radius, Ri is the inside radius. Okay, this one and this one. Let us say the heat transfer coefficient at the inner surface of the tube is Hi and at the outer surface of the tube is H naught. So the convective resistance or convection is 1 by AiHi, right, inside, and R convection out is 1 upon A naught H naught. If we write it fully, this will be 2 pi Ri L Hi 1 by 2 pi R naught L H naught. So R total, if we draw the electrical circuit for this one, this will be something like this, right? This is our surface. At this point we have some convective resistance, then the wall resistance, and again the convective resistance. This is nothing but 2 pi Ri L Hi. This one is ln of R naught upon Ri upon 2 pi KL, and this one is 1 by 2 pi R naught L H naught. So R total is equal to 1 by 2 pi Ri L Hi plus 1 by 2 pi R naught L H naught plus ln of R naught upon Ri upon 2 pi KL, because all these resistances are in parallel. Okay. Now if we see here, we want heat loss from hot fluid to cold fluid. To happen this, we will choose a material which have as high thermal conductivity as possible for the inner tube. So here K is very high, and if the thickness of this inner tube is very small, that is, if R0 is equal to Ri, and for high heat transfer rate, thermal conductivity has to be higher. If this is the case, then this term will go to 0, and then we can write R total is equal to 1 upon AiHi plus 1 upon A naught H naught. Or in terms of total or overall heat transfer coefficient, U, right? U is nothing but 1 by A R total. From here we can write 1 by AU is equal to 1 by AiHi 1 by A naught H naught, and since Ri is approximately equal to R naught, this implies Ai approximately equal to A naught, that is 1 by U is nothing but 1 by Hi plus 1 by H naught. This is important. Remember this. As the time passes, performance of a heat exchanger deteriorates with time as a result of accumulation of deposits on heat transfer surface area. If we consider the surface, okay, so after some time there will be some deposits on the surface. Let us say this is something like this. At both the surfaces, I am only drawing at bottom surface. Okay, so this is the deposition. We say this is the deposition or accumulation of deposits. These deposits will cause one additional resistance. This will cause additional resistance to heat transfer, and this resistance to heat transfer due to deposition is given by falling factor. This accounts for additional resistance offered to heat transfer due to accumulation of deposits on heat transfer surface. So falling factor is represented by Rf, and the thermal resistance due to thermal resistance due to falling is given by Rf upon A. Okay, so if we rewrite the total heat transfer or total resistance to heat transfer, it will look like this: falling factor at inside surface upon Ai plus ln of R naught upon Ri upon 2 pi Kl plus Rf naught upon A naught plus 1 by A naught H naught, and the overall heat transfer coefficient 1 by UA will be 1 by AI. Okay, if I say 1 by UI, AI is equal to 1 by U naught, A naught is equal to 1 by U R total or A R total, right? If we see here, this is U naught A naught, so this will be U A. Okay, and 1 by UA, this will be R total.